Hey everyone, Ms. Caulfield here. In this video, we are going to be looking at how to perform different calculations using significant figures. So when we're doing labs, you are often going to be collecting measurements of some sort. And after you've collected your measurements, which is going to be your raw data, sometimes we're going to have to do some math with that raw data in order to extract some meaning from the data that you've collected. But when we do the math on a calculator, we can report many decimal places. But when we look at our lab equipment can't measure as many decimal places as our calculators can give us. So we want to make sure that when we are reporting our answers, that we are making sure to represent the precision of the equipment we use in the lab. So this video is going to be looking at how to perform different types of calculations and round your answers to the proper number of significant figures. Before we get started with that, we are going to review how we determine the number of significant figures in different numbers. So looking at our first example here of 12.000, we recognize that this number has 3 trailing zeros. And we remember from our rules that trailing zeros are significant only if there's a decimal in the number. So since we see the decimal in this number here, those trailing zeros are significant. We've got 2 non-zero integers, so this value is going to have a total of 5 significant figures. In our next example, we see again that we've got some trailing zeros, but we also have a leading zero. And we remember from our sig fig rules that leading zeros are never significant. There's no contingencies on that. They are never ever significant. So anytime you see a leading zero, you can go ahead and put an X through it. That is not going to be a significant figure. But because we do have this decimal in this problem, those 2 trailing zeros are going to be significant based off of the first rule that's written on the bottom of the screen. So this value is going to have a total of 3 significant figures. Looking at the next problem, we see that we have another trailing zero that we're looking at. And we've got some leading zeros here. And just like in 0.100, we can go ahead and put an X through all of those leading zeros because they are never significant. Because we do have the decimal in this number here, this trailing zero will be significant, which leaves us with a total of 4 significant figures in that number. And in our last example, 4,500, again, we see more trailing zeros. The difference here is that there is no decimal in this number. And so looking at that first rule, trailing zeros are significant only if there's a decimal. So since there's no decimal, these trailing zeros at the end are not going to be significant and will only have a total of 2 significant figures in this problem. The third type of zero that's not mentioned here is what we call a captive zero. And captive zeros are always significant. An example of a captive zero is going to be 701 or 7001. In these situations, the captive zeros are always significant, and so we would have 3 sig figs and 4 sig figs respectively in those 2 numbers. So the first type of math that we're going to be looking at is addition and subtraction, and our sig fig rules regarding addition and subtraction. So when we're thinking about addition and subtraction, we are limited in our answer by the least precise number in the problem. So the least precise number in the problem is going to be the number that has the fewest digits after the decimal place. So if we look at these 4 numbers in the problem here, we see 20.4 plus 1.32 plus 83 plus 0.6. And when we add those all up, we get 105.32. Well, you want to go ahead and line up the decimals in the problem so that you can identify easily which one is the least precise. And the least precise, again, is the one with the fewest digits after the decimal place. So the least precise number in this equation, or in this problem, is going to be the 83, because 83 has no numbers after its decimal place. It doesn't even have a decimal. So since it is the least precise, we see that our answer has to match that precision, and 83 is precise to the ones place. And so when we round our answer, we need to round our answer to the ones place. So we see that our unrounded answer is this 105.32. We're rounding to the ones place, so we have to take a look at the digit next to the ones place to see if it's going to cause that 5 to round up or stay the same. Remember, if it's 5 or above, give it a shove. So if it's 5, 6, 7, 8, or 9, it would cause that to round up. If it's 4 or below, let it go. So if it's 4, 3, 2, or 1, or 0, then it's going to stay the same. So that's how we get our final answer of 105. So let's go ahead and practice 2 of these problems. The first step, like I said before, is to line up your decimal places. So we have 1.2 plus 0.13, and then you're going to solve your problem. So you end up with 1.33. Then you want to take a look for the least precise number. So you'll find the one that has the fewest numbers after the decimal place, and you can draw a line down. So I see that my answer has to be precise to the tenths place. I have to round it to the tenths place. So I can keep this one in my answer, and I can keep this 3 because that 3 is in the tenths place value. Then I have to take a look at this last digit next to it to see what it would cause the first 3 to do, if it would cause it to round up or stay the same. And we see here that that 3 is going to cause it to stay the same, so our final answer, rounded to the proper number of significant figures, would be 1.3. All right, let's go ahead and try the next one. So we've got 0.0012 minus 0.0008. When we solve that, we get 4, so 0.0004. When we line up the decimal and we draw our line, we see that all 3 of those numbers are equally precise because they are all precise to the 10,000th place. So our final answer would be 0.0004. We wouldn't have to do any rounding on that one. Now that we've looked at the rules for addition and subtraction, we're going to take a look at the rules for multiplication and division. I personally think the rules for multiplication and division are a little easier to remember than addition and subtraction. So that rule for multiplication and division is that when we solve these problems, we are limited by the fewest number of sig figs. So whichever value in our problem has the fewest number of sig figs, that's going to be what's limiting our answer. All right, so when we take a look at this problem, 44.4 times 0.17, we see that our unrounded answer is 7.548. Then we have to go back to our problem and we have to identify how many sig figs each number in the problem had. So 44.4 would have 3 significant figures because they are all non-zero integers. 0.17 would have 2 significant figures because that leading 0 never counts as a significant figure. So when we compare those 2 values, 2 sig figs versus 3 sig figs, we are going to be limited by the number with the fewest amount of sig figs. So since 0.17 only has 2 significant figures, our answer can only have 2 significant figures. So just like in the addition and subtraction problems, you're going to start at the left-hand side of the number, and you're going to ask yourself, can I keep this number? Do I have enough sig figs for it? So our first number would be the 7, which you can keep, and this would be your first significant figure. Then you'd ask yourself if you can keep the 5, which would be your second significant figure. And remember, we're only allowed to have 2 in our answer, So then you'd have to ask yourself, can I keep this 4? And the answer would be no, because that would give you 3 significant figures. So then you have to think about, what does that 4 cause the 5 before it to do? Would it cause it to round up or stay the same? And since it's 4 or below, it's going to stay the same, and our final answer would be 7.5. So let's go ahead and practice 2 together. So when you plug in 1.2 times 0.13, you end up with 0.156 as your answer. Then you need to identify how many significant figures each number in the problem has. So 1.2 has 2 significant figures, and 0.13 also has 2 significant figures. So my answer has to only contain 2 significant figures. Remember, the 0 is not a significant figure because it is a leading 0, so we can go ahead and write that if you'd like, or you could also just write the decimal. Can I keep the 1? The answer would be yes. This would be our first sig fig. Can I keep the 5? The answer would be yes. That would be our second sig fig. Then we have to look at the 6. I can't keep that because that would give me 3 significant figures in my answer. So then I have to ask myself, what does the 6 cause the 5 to do? And it would cause it to round up. So instead of having 0.15 as our answer would need to become 0.16. Same thing with the problem below. So when you do 485.369 divided by 0.124, you end up getting 3,914.26613 as your unrounded answer. And we're going to go through and do the same steps that we did with the top problem. So this first number has 6 significant figures in it. The second number has 3 significant figures in it. So I'm limited by the fewest number of significant figures, which means I can keep 3 significant figures in my answer. I can keep the 3, which would be my first significant figure. I can keep the 9, which would be my second significant figure. I can keep the 1, which would be my third significant figure, but I can't keep the 4 because that would give me 4 significant figures. So then I have to ask myself, what does the 4 cause the 1 to do? And it would cause the 1 to stay the same. But 391 is not quite the same as 3,914. So we have to add something as a placeholder that would not count as a significant figure. So at the end of this number, we're going to go ahead and add a 0. Since there's no decimal, it means that that 0 is not significant, but it does help maintain the number's integrity. So instead of it being 391, it's now 3,910, which is more representative of the number that we were looking at here in the first place. So now that we've had a chance to look at the rules for addition and subtraction and multiplication and division separately, we're going to go ahead and do a couple of practice problems where we look at them together. So when you're looking at multiple operations in a problem, you want to make sure you're following the order of operations and solving the problem just as it's written. So for the top problem, you would start by doing 1.265 plus 1.02, which gives you 2.285, and you'd be multiplying that by 82. So my unrounded answer for the top problem would be 187.37. Actually, I'm going to rewrite that up on the line. 187.37. So you want to make sure you find the unrounded answer first, and then you're going to think about each step of the problem. So for this first step, I did 1.265 plus 1.02. And if I were to solve just that part of the problem, I would get 2.285 as my answer. Well, if I was thinking about the rules for addition, I would see that I would have to round to the hundredths place because the least precise number is 1.02. So I would have to round to this place value, which would give me 2.29. And 2.29 has a total of 3 significant figures in it. Well, I would then have to think about the next step of the problem. If I did 2.29 and I multiplied it by 82, which has 2 significant figures, in that step of the problem, I would be limited by the 82 because it has the fewest number of significant figures in its value. So ultimately, I would have to round my answer to have 2 significant figures. So if we round 187.37 to 2 significant figures, we get 190 as our answer. All right, we're going to look at one more and then you guys will be done for the day. So looking at this next one, we're going to do 1.2 times 4 first, and then we're going to add that to 35.1. So my unrounded answer is going to be 39.9. And then I need to break the problem down. So if I look at the first part of the problem, where I did 1.2 times 4, I see that 1.2 has 2 significant figures, and 4 has 1 significant figure. When I solved this part of the problem, I got 4.8 as my answer. Well, I would have to round that 4.8 to 5 to match the fewest number of sig figs in the problem. Well, then if I was to take this 5, which has no decimal places, and I added it to 35.1, I would see that my answer has to be precise to the ones place, because the least precise number in this part of the problem is the 5. So then that means that we have to round our answer, this 39.9, to the ones place. So when we round it to the ones place, we end up getting 40. But 40 is not showing precision to the ones place because that trailing 0 right now is not considered significant. If I add a decimal right here, now that 0 is significant. And I know that you guys may not be familiar with seeing a decimal after a 0 like that without adding another 0 or multiple zeros after it, but it is okay to write it like that. And here that it would be how you would have to write it in order to get the precision to the ones place.